Hello, everybody. My name is Torsten Hoefler. I am joining you from wonderful Switzerland, from ETH Zurich to be precise, and I'm glad to present this keynote at the DIS conference. Unfortunately, I cannot be with you, or we are not really allowed to meet, but I think this is also going to be fun, so let me start right away. And my first item on the list of things I want to communicate is that I want to thank Hagit Attia not only for inviting me to this keynote, but also for teaching me pretty much, for teaching me indirectly pretty much everything I know about the field of distributed computing, and by writing her book also together with Jennifer. To just introduce me a little bit more, I am a practitioner. I've been working mostly on the field of high performance computing, very large scale high performance computing, more than 1,000 nodes, as we will see usually. And there I've been contributing most to the message passing interface, where I've also been contributing to a book. And this is something that I will actually emphasize the message passing interface through this talk with a whirlwind tour through multiple different research results, then diving deep into one specific result, which I find most interesting in the context of distributed computing, and then continuing with the data center and the future and how high performance computing and data center computing is going in general. So let me get the laser pointer. So what is the message passing interface? So what is really what we are talking about, or what I just introduced? So the message passing interface is a set of communicating processes. We could call those communicating sequential processes, but they're usually not sequential because each of those is often multi-threaded. So here we have 5 processes, and each of these processes has local memory. That is quite important. That local memory is isolated from the other processes. And each of these processes is asynchronous. So it runs at a different speed and makes different progress. And this is quite important. And then, of course, when it comes to distributed computing or message passing, these processes send messages to each other at various times. That is also non-deterministic and asynchronous. But now, each computation in these processes, so each of these processes executes a specific computation. And what we can do is we can model this computation as a computational DAG. And at the end, all of these processes, the way I would see them, are simply communicating computational DAGs. So there are vertices that are operations, there are edges that are data dependencies or data movement between these operations, and then there are communication vertices that send messages to other processes in a different memory space. So this is really the most abstract and most powerful model we could use here. And then at the end, we have a distributed, or in more theory terms, a cut computational DAG that is now cut into these different partitions, process 0, 1, 2, 3, and 4. And then all the communication edges, all the edges that are crossing between different processes is what we call communication edges. They go and actually send messages, which is at the end going to use MPI. But actually, we could scale this down to simply the overall DAG without the distribution. And then the major theoretical problem lies in actually deriving the distribution or deriving the cut of this graph. So if I give you this graph, how would you cut it? And of course, it's still laid out like it was before, so it's relatively simple in this example. But in general, it's actually quite hard. So I would like you to keep this in mind as we go through the talk, because it's actually quite hard to work with these computational DAGs. And this is really the high art of message passing and parallel programming in general, to understand the structure behind these DAGs and to map them well to target devices. So, but what do these DAGs mean? We can go a little bit more into detail, and I'm expecting that most of you know this. This is why I will actually go quite fast here. But how do we conquer the complexity of these computational DAGs? Here on the right side, we have one of those DAGs. It has a start node and an end node and multiple intermediate nodes. So first of all, we can characterize the work of this DAG, which is simply the number of operations or the number of vertices. So it's quite simple. But then the next metric is actually the length of the longest path in this DAG, which is which is also called the depth, and that is the minimum time required to execute this DAG on a very large, even on a very large scale machine, because that is the longest dependency chain we have that has to be executed sequentially. But now getting to parallelism, we can now also characterize the parallelism either through the parallel efficiency or through some measure of maximum parallelism, where we just look at various level cuts of this graph and count the number of vertices that are there. Here in this case, 1, 2, 3, 4, and 5. So we can use at most 5 different processes here, even though it's still relatively inefficient because the longest path is actually longer than that. So it may or may not be efficient to parallelize this, but we can measure it with the parallel efficiency. Furthermore, the interesting insight is that these graphs usually have small tree width because they're very often serious parallel graphs, but this is something that needs to be determined for the specific graph at hand. The major insight is that the generating program has an O of 1 description because humans have to write it, right? So this is now an execution DAG, but the generating program that generates this graph is relatively small. So getting to these generating programs is, how do we now analyze these CDAGs? How do we reason about the programs that generate those, not about the CDAGs themselves? Because we can easily count these vertices. But if I give you this code, for example, that of course during the execution generates a CDAG, but the description is relatively small. If I give you a large n here, I could give you a trillion as an n, then this graph, the resulting execution CDAG would have a trillion vertices, or even more than a trillion vertices in this case. So you can actually think about the runtime complexity while I'm talking. How many iterations in terms of n does this loop, this nested loop do in brackets, how many operations are executed here. So we can actually model this in an affine loop model that I don't want to spend too much time on. In fact, one of my students, Greg Kwasniewski, was working on this for a while. And if you care about details, you could look at this paper down at the bottom. But what we can do is we can model these loops, these looped structures, as relatively simple mathematical constructs if they fulfill some constraints. The major constraint is that the update is affine, which you can see here. In both cases, they are affine. Then we can model the loop update, the loop guard, and the initial assignment. We can even model this for arbitrarily nested loops. And then we can compute the runtime for this loop. So this gives us an immediate insight into automatic work depth analysis for MPI and other explicitly parallel programs. So this is an interesting result that I don't want to dwell on too long, but this helps us to conquer these computational DAGs, as I mentioned. So now getting back to something practical, we have these extremely large machines. So this is a machine that I helped to construct in 2012 before coming to Europe while I was still a professor at University of Illinois. The total cost of ownership is about $500 million, including personnel, hardware, and operational costs such as energy. In fact, the capital value of this machine is about $208 million, so a little bit less than half. It has nearly 50,000 cores and half an exabyte storage. But now the question is, these processes that I showed you on the first slide, where do they go? So they're somewhere mapped on this machine, but this machine is incredibly complex. So what is the major complexity of this machine? Well, the major complexity is how are these processors, which are pretty much normal CPUs here, these bulldozer CPUs you could buy, well, not anymore, but in 2012, you could just buy them in your favorite store. And the server architecture is relatively simple. But how do we now connect those? And this gets me to a little bit of an overview how machines have been connected and will be connected in the future. So starting in the 1980s, machines were actually pretty simple structures connected by very low dimensional torus networks because it's quite obvious how to map them in real space, as you can tell, right? In this case, it's just a 2D mapping. Then later, machines, due to the lack of bandwidth, of global bandwidth in these architectures, they were actually moving towards more complex, high bandwidth or full global bandwidth, or sometimes also called non-blocking structures, such as the Clos network or the fat tree networks, as we can see here. Actually, the Clos network comes from telephony in the 60s, but the fat tree network is really the most popular network today. But then at around 2005, network technologies changed. So we moved from electrical networking to a partially optical networking because of distance and speeds. And there was a new topology, the Dragonfly interconnect, which was actually quite, it's a quite interesting interconnect. It's, from a graph theoretical perspective, it's a clique of cliques. So we have these grayish vertices, so each vertex is an endpoint. Those form fully connected cliques, and then among those, they're again fully connected. So a clique of cliques, which is what is now going to be the exascale interconnect. So we have a paper on the slingshot interconnect, which basically uses that Dragonfly topology as we are moving forward towards exascale. Then if you take this to the extreme, so this is an engineering solution, so this is cheap and good, but if you take this to the extreme and solve the mathematical problems that are underlying these graph structures, you come to a structure that we call the slim-fly network, which is really about getting the diameter of the network as low as possible. And then we can save up to 50% over the fat tree that I mentioned before, over about 33% over the dragonfly. But unfortunately, it's extremely hard to construct. So I will leave it with this, just that you get a little bit of an overview of the complexity of how these computers are connected, because that is one of the major aspects of design today for high performance computers. In fact, also for data centers. So data centers use something very similar to fat trees today, but they're most likely going to move to more complex data center topologies because they're simply more efficient. As I've told you, it's about a 50% efficiency gap. But now, if we go back to these MPI processes, now you understand the structure of how computers are built in these data centers. So they're connected with rather complex topologies. And now the question is, how do we now map an MPI program that has also a topology, but it's a communication topology, to those data center nodes? And the MPI specification has done a specific, has made a specific decision where they say, well, the MPI program specifies its communication topology, but does not learn about the underlying system topology. So here I have a program with 4 processes, and the communication topology is that 0 sends to 3, 0 sends to 1, and 3 sends to 2. So a very simple graph. And now let's assume we have a 3D torus here, or a hypercube, depending on how you want to see it, with the numbering as indicated. And we want to map this graph somewhere onto this graph. So one possible mapping would be to map process 0 here, to map process 1 here, process 3 here, and process 2 here. But now if we look at the communication, process 0 communicates with 3, 0 communicates with 3. So this edge here is occupied by this communication link. And then 0 communicates with 1, and 1 is routed from here to here to here to here, because 1 is actually a pretty large distance in our mapping. Then we can see already that this cable, this physical network cable, is used twice in this particular mapping. But now, of course, you can have a different mapping where you map 0 to this node, 1 here, 3 here, and 2 here. And here you have no cable used twice, and also the average distances are better. So it's pretty clear that gamma 1 is worse than gamma 2 from the assignment of these processes to this particular topology. In fact, we can formalize this. There's a notion of dilation, which is really the average extension of any edge. So how much further do I have to go? So if I'm communicating from 0 to 1, here I have to go 1, 2, and 3. So this dilation would be 3, then the direct connection. So this is also a measure of communication work, right? Directly proportional to the energy consumption of the network. And then, as I mentioned, this is computed by looking at every single connected edge in the host graph, and then computing the dilation. So what is the distance in the target graph? So then we could also measure the congestion, as I already pointed out here. So congestion is basically how many links, how many messages here in this graph are using the same physical link in the target topology. So this is somehow a lower bound to the time of the communication, because if these are all unisize messages and I have a congestion of 2 here, then I get at most half the bandwidth over the execution of the program, and then I have to invest more time to actually communicate between these processes to fulfill this communication pattern. So this is MPI's way of mapping. There are many approaches to do this. Unfortunately, the general topology mapping problem is NP-hard. It's relatively easy to prove as a partition problem. I don't have time to do this now, but it's actually proved in this paper that I'm citing below. And it is so hard that there are already survey papers of the various different techniques. And I just want to give you one interesting technique now that I quite enjoy, because it's extremely efficient and reasonably high quality. So by extremely efficient, I mean that if an MPI program is running on the machine itself, we need to adopt this mapping during the runtime of the MPI program. So we don't have too much time. If we take hours to do the mapping and the program takes only minutes to solve its task, then this would be quite inefficient. So here we have an application graph. It's a sparse matrix vector multiplication of a particular matrix. And on the left side and on the right side, we have the network graph, which is an 8 by 8 by 8 torus. You see this is less regular because it's a real world object. It describes the neighborhood relationships in a real world object. This network graph is very regular because it's really just a 3D torus. So what we now do is interesting that we minimize the bandwidth of these matrices. So here we can apply an RCM, reverse Cuttle-McKee. We get a permutation of the rows and columns of this matrix, but now the bandwidth is minimized. We can do this on the right side as well. We minimize the bandwidth, we apply the reverse Cuttle-McKee algorithm, and then we get this interesting visualization. But now we can map these two onto each other. And now vertices that are close here are somehow mapped to vertices that are close here. And the intuition is that they will get high bandwidth links. And in fact, this is working for these graphs. So as you can see here in this plot, it plots the congestion over the number of nodes for this particular mapping from 64 to 1,700. And we have different schemes, like the greedy scheme, which is just greedily mapping address, this reverse Cuttle-McKee that I just explained, and the recursive scheme, which is doing recursive cutting into equal-sized pieces. And we can see that all of those are performing approximately equal, I would say. They all improve about 10 to 20% over the initial mapping, which is somewhat random. And this is just a simulation, and here is a real benchmark where we see the same result. So on a 512 node 3D torus blue gene machine, we actually get about a 10 to 15% improvement in the communication time by applying this mapping. And the interesting thing is not the improvement of communication time, of course, is necessary, but it's the runtime. So we can do this during the runtime of the algorithm. And we see here that the greedy and the recursive and a threshold accepting scheme, which is much slower. Here is the runtime in seconds over the allocated nodes again. The RCM scheme is always faster than 10 milliseconds, which is the resolution of the timer. So it's extremely fast, and it's more like 20 times faster than the next faster greedy scheme. So we can see that we can actually do this at runtime. So there is still a lot to be done in this topology mapping area. There's a lot of potential where smart people like you could immediately get interesting impact in the field of high performance computing by just mapping these two graphs onto each other. But of course, it has interesting constraints. We need a quality constraint, but also a time constraint. It needs to be relatively fast, this mapping. So we cannot wait days. So it's not an operations research problem. It's really trade-off between mapping time and mapping quality in general. So now let's assume that our processes are mapped nicely, and we go towards executing a program. So now we have our processes, they're mapped to the right machine. As I told you, it's a little bit of a whirlwind tour. Now we're getting to the next stage. This generating program has an O of 1 description because some human has written it. So which means it has a lot of structure inside. In fact, it has so much structure that we can explain it, or we can model it by a bulk synchronous process where all processes move in lockstep in the same in their same local state, which is quite nice. And MPI supports this. MPI does not force the bulk synchronous model. It's a common misunderstanding. MPI just supports the implementation of programs in BSP by offering a whole lot of collective communication routines that we could now all discuss, but I don't have time to discuss all 17 of those. I introduced some of them, the later ones, the neighborhood collectives, for example, were added in MPI 3, but I want to focus on one of the simplest ones, MPI broadcast. Very simple problem, very related to the broadcast problem that you know, and you know I'd love, I'm sure, as an introductory problem. But now the question is, how do we make fast broadcasts, which is slightly different from the typical the typical distributed systems community view. So how do we get a minimal latency broadcast? For that, I want to introduce a model, the so-called log-P model, which is a model of communication in a network. How does it work? Well, we have a source process and a destination process. I'm going to tell you about a ping pong process. So the source process sends a message. It takes time O. Then the message travels through the network. So CPU overhead O. It travels through the network in latency L. It's received at the destination, again, takes time O. The destination sends a reply message, which again takes time O. The message travels again the same latency L through the network and is received at the source. So we have had a full round trip. The round trip complete time is 2 times L plus 4 times O. Very simple, very, very simple model. Actually, we have a benchmark where you can benchmark real systems to get their log ops parameters. There are some more parameters that are a little bit more intricate, like these Gs, but I want to skip them for this talk to just give you an overview of this. And then we have a simulator where you can simulate executions in that model just to get relatively exact, so 5% error results with respect to a real execution. So, but now let's see how we can design a broadcast algorithm in log-P. So a broadcast algorithm is really an algorithm where one node, one process in MPI has a value, and we want to distribute it to all other processes. In this case here, we have a latency of 2, an overhead of 1, and 7 processes. The simplest algorithm would actually just send it to the next, 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 which would always give us a difference of 4 time step between those processes, and we would get a total time of 24. And now you're, okay, yeah, this is extremely inefficient. We know that we can do it with a binary tree. Well, a binary tree, starting time 0, the first one receives it after 4, the next one after 5, because we have to wait 1, 0, and so on. So great. But I am telling you that you can do this better than a binary tree, because the first process only sends to 2 neighbors and then stops sending. But it could actually continue sending, like in this animation here. And then we finish after 9 time steps. So this is what we would call a binomial tree. But now I can tell you, you can even do it better than a binomial tree if you take the exact numbers, the L of size 2 and the O of size 1 into account, and pipeline it in a way that really optimizes to this L and O. So I don't have time to explain it in detail how it works, actually not super trivial, but this is something that is a generalized Fibonacci that we call, the community calls a generalized Fibonacci tree. And this gets, in this particular example, finished after 8 time steps. So 1/3 of the original time, of the trivial time. The interesting insight here is that this is actually, this Fibonacci tree, the optimal tree in this case, can be up to 40% faster than the binomial tree, which is what most people use. So model-driven optimization of these algorithms is extremely, or can be extremely important and extremely beneficial. And we will get back to this later. But here in the distributed systems community, people often worry about failures. Not so much in the HPC community, but this is coming. So we are actually converging on this area. What happens if processes fail? So we have our processes here, again, the same ones as before. Let's assume process 3 fails. What do? Well, in fact, it's very likely that these processes fail. Already in 2010, people were discussing that a petascale system will only be up for 1 hour approximately. And this does not happen. Petascale systems are up for about a week. The system I showed you in 2012 that had a mean time between failure of about a week. In 2011, then they mentioned next generation systems are even more problematic. Exascale systems now, so this was all set in the context of petascale, but exascale systems now will fail every 10 minutes. So there are many, many studies on this. I doubt that nobody will be able to sell a large machine that fails every 10 minutes. However, I think it is getting more and more prevalent, more and more important to react to errors, and especially in the data center context, as we will see. So there are some differences, because in HPC, you can always do checkpoint restart. In data centers, not so much, because you don't want to lose credit card transactions. So now let us work on a fast, low work, fault-tolerant broadcast. So fast, energy efficient, low latency, energy efficient, and fault-tolerant. So a very simple solution to the problem would be to just use a gossip algorithm. So the gossip algorithm is relatively simple. We send, like the root node starts sending the node, the information to a random other node. Upon reception, the random other node sends it to other nodes and so on. There is nice theory to it, but unfortunately the theory does not guarantee consistency. So if we run this the simulated theory, we will only get a 95% consistent result. So what does consistent mean? Consistent means that in fact all processes received the broadcast. So in this case, I'm launching an MPI broadcast here. The first round, all processes receive it. The second round, I'm launching an MPI broadcast from node 3, and node 0 does not receive it. Then I do some compute. Node 0 did not receive it. Then the set of processes that received it continues, because this process is still waiting for, because MPI is a synchronous interface. And then they launch another collective, a reduce. And now this reduce is waiting for the input of rank 0, which is still hanging in the broadcast. And unfortunately, now I'm deadlocked essentially, so I cannot move forward. This is due to the fact that we are simplifying the programming model by assuming that every process is participating in every single collective operation. So BSP style does not work if it's not consistent. But now the question is, well, there are fault-tolerant MPIs, so how does that work? They don't use gossip today. So what can we do? Well, we can use a dynamic tree, for example, which is extremely intuitive. So the message is sent down the tree, and once it reaches all the leaves, of course, everybody knows who's a leaf. The leaves send messages back to the root, and so everybody knows that it's a consistent execution. If something fails, the root just restarts the tree with a new with a rebuild protocol. So we have at least 2 times log n the depth, because we need to go down and up again. But now you may already heard that there is another way to implement this for high-performance computing applications, like what OpenMPI has chosen. So the previous slide was what MPI-CH, one MPI implementation shows. OpenMPI is using a so-called binomial graph, which is log2 fault tolerant. So it can tolerate up to log2 many errors. The previous one can tolerate an arbitrary number of errors with rebuilding. This one is actually using a graph where every node sends to log n many other nodes. And this is why we have a log n. And of course, upon reception, that new node sends again to log n many other nodes. And this is why we are resilient to up to log n minus 1 failures. So, but both are quite far from optimal, both of these approaches, right? They're well known in the community. But what I want to discuss now is actually we are using the power of randomness as gossip, but not just gossip. So we use gossip, but then after we have gossiped for a while, we switch to a deterministic correction protocol. So in this sense, we're turning a Monte Carlo style gossiping algorithm into a Las Vegas style deterministic algorithm. And this is the interesting insight. Of course, the definitions are all the same as in the standard textbook for the fault-tolerant broadcast. So integrity, no duplicates, non-faulty liveness, and faulty liveness. You can read the definitions here. It's not particularly hard, but all of these guarantees are given by the broadcast. We do relax 3 and 4 a little bit. We have 3 different consistency stories here. So we either say it's not consistent, like in the normal gossip case, our algorithm is slightly faster. We could say it's nearly consistent when we have a bounded number of errors. And we have, of course, also a fully consistent version, which is, of course, most expensive in that context. So let me present you the key idea. So the first one, the first algorithm we call opportunistic corrected gossip. So corrected is the important aspect here. So what do we do in this algorithm? This algorithm, we send messages in gossip style to random nodes. But we already realize here in this animation that node 5, for example, receives the same message 3 times. So it's incredibly inefficient. We have lots of redundant messages due to the randomness, especially if you run it to the end. Most nodes will already have seen the message, but will still get it because of the random allocation. And here you can see a plot where we have the time on the x-axis, the runtime, and the number of reached nodes. So you see the optimal algorithm, which is the Fibonacci tree that I told you about earlier. Right, that reaches after 20 time steps, it reaches all 1024 nodes. But then the gossip algorithm becomes quite inefficient because after we have reached 50% of the nodes, we will very likely send to random other nodes that have already received the message. So we somehow want to avoid going here because hitting the last nodes is actually quite unlikely and quite expensive in practice. So you have to run it quite a long time until you get really consistent. So, and what we are proposing here is actually that we run the gossip for a while, right? We will define what a while means, and then switch to a deterministic ring correction protocol. By a ring correction protocol, every rank just sends it to the next node. So let me animate this here as well. So we have the same gossip phase. And now the gossip phase ends and we have reached all the blue nodes, but we have not reached the green nodes. So how do we reach the green nodes? Now every blue node that received the message sends it to its right neighbor. And now sends it, the newly received node sends it to the next. And now we have reached all nodes, right? Messages may be received twice, once during the gossip phase, or many, many times actually, many times during the gossip phase, and once again during the correction phase. But now the question is, what is the latency of this? When do we have reached all nodes? In other words, what is the longest uncolored chain that I have to traverse in the correction phase? Because in the extreme case, if I don't gossip at all, I would be back to the worst case or the simplest algorithm with the 24 time steps that I showed you before. So now the question is really, how long do I have to gossip that this longest uncolored chain is of reasonable length? Well, you can simulate the size of the longest uncolored chain here in this K. So of course, at the beginning, you start with all of the nodes, essentially n-1 here, 1023. But then it drops relatively quickly as gossiping moves forward to a relatively small value. And somehow here, you want to switch because this is very, very small and gossiping becomes inefficient. So somewhere in this area, you can actually, and this is a 99% probable chain of a simulation. So you can actually compute this. We can approximate this with equations that I don't want to go into detail. You find them in this paper down here. And we can compute an approximate good starting time for the correction phase. So here in this case, we plot the total execution time of gossiping plus correction versus the gossip time. So if we gossip very little, like none at all, basically, the total time is very high, of course, because we have just a linear broadcast. If we gossip a little bit, we will get to this lower piece, but then gossip gets inefficient, right? And here we have our model as the line and our simulation as the points, and we see that's about 24 steps here, and we have a closed form equation where it really depends on L, like the latency, the CPU overhead, and the number of processes. Very much, again, the log P model that I mentioned before. But now, as we mentioned, it is more efficient, but does not guarantee that all nodes are reached, because if I now this node fails here, and we do the gossiping again, and here we have now these gossip nodes we send to neighbors, and now unfortunately node 3 is not going to receive the broadcast. Right? So it's not always consistent if we have failures. It's relatively good, but not 100% consistent. But now let's move to another algorithm, which we call the checked correct gossip, which is slightly more complicated. So we want to send, we do the same gossip phase, but then we send it to the next node. Each node that received it during the gossip phase sends it to the next, and then the next, and then the next. So it's not passed on by the node, but it's passed, the original node sends it. So in this case here, we have these nodes that are reached via gossip, the blue ones again. They send it to the next neighbor. Then the same node sends it to the neighbor 2 away, same node 3 away, same node 4 away, basically until it has heard from another node that the cycle is closed, right? So it now knows that it has reached all the nodes for sure, right? So it guarantees, because we are waiting, we keep sending in this direction until we heard from node 4 here. I mean, node 0 keeps sending until it got a message from node 4, and then it knows, oh, hey, I've sent to node 4, I've covered this half of the circle, and then node 4 has covered this half of the circle. Relatively simple, and it's actually consistent under the assumption that during the correction phase, none of the gossip nodes fail. Okay, so here we can do a similar simulation. We have to run the gossip phase a little bit longer because we want to reach more nodes, because now these nodes do a little bit more work, but basically the same as we had before. So now, as I mentioned, if we fail during that correction phase, if a gossip node fails, then we may still have the case that not everybody is reached. So now if we want the fault tolerance for f+1 or f nodes failing, what we have to make sure is that we have at least f+1 gossip nodes, because if one of the gossip nodes survives, they will just go towards the end. And so we run our protocol in the case that we, in this case, that we, until we know that f+1 other gossip nodes have received the message, right? And then are sending it on, of course. So, but now if there are less than f+1 nodes you reach during the gossip phase, this is the probability of this is basically 0. We have never seen this in any of the trillions of simulations we have done, but you could imagine such a case. In that case, if a node cannot find f other gossip nodes, then it'll go into panic mode. After a timeout, it'll basically start sending to all nodes a special message, including the broadcast, that puts all other nodes into panic mode, where now we have an all-to-all broadcast. So everybody now sends to everybody. But again, this is a hypothetical case. This will likely not happen in practice. The Earth may also explode, probably with the probability as high. So extremely unlikely. But we can now formally prove correctness under this assumption. So we have these 3 different algorithms that are going from less consistent to fully consistent, but they're also growing complexity. So now let us compare the algorithms on a specific machine, the TSUBAME 2.0 machine, where each node has an MTBF of about 18,000 hours. And if we assume a 12-hour run on 4,000 nodes, we have about 3 failures during that 12-hour run. So here we have these different algorithms: gossip, the optimistic, the corrected, and the fully corrected implementation that I just showed you, our algorithms. Here we have the binomial graphs, and here we have the tree algorithm that I explained to you at the very beginning. So these 2 are existing algorithms. Here we run them with 0 failures and 3 failures. So each of those, now we compute the optimal gossip time in time steps, and then we get a latency out of the simulation. So in this case, gossip runs 53 time steps, optimized gossip or opportunistic gossip 42, corrected gossip, it's a little bit slower, fully corrected gossip, again, a little bit slower, but they're both faster than the binomial tree, because it has to send log n messages, and the corrected tree because it has to run down and up. So it's 2 log n here, so very expensive. In case there is a failure, it even gets more expensive because it needs to repair the tree and do the whole thing again. So the work is now the number of messages being sent. So here the gossip algorithm is the worst because it needs to send a lot of redundant messages. The optimistic gossip reduces it to less than 40%. The corrected gossip goes even a little bit further, and then the fully corrected, again, it needs to reach f+1 or f other nodes, so it needs to send more messages. And this is much better. All of these gossip algorithms are much better than the binomial tree, which sends log n additional messages from each node. But the tree itself is actually best in terms of work because it sends really the minimal number of messages. Well, okay, 2 times the minimum number of messages. And we will see in a couple of minutes that we can actually use this insight. And then the inconsistency is basically over a very large number of simulations. We are computing the error rate, meaning that not all nodes are have received the message. Here in this gossip case, it's well 10 to the minus 6. Here in this optimistic case, it's a little bit higher, but we could adjust it by running the longer gossip phase. But we are suggesting CCG anyway, if you want consistent systems where you have a 0% rate, essentially. I mean, the hypothetical case that these 3 errors in the 12 hours happened during the correction phase did not happen in our particular simulations. So, and all the data is within 2% of the median here. So now if we look at the latency, with respect to the number of nodes, we can see the optimal algorithm is best, of course, because it's optimal. Our gossiping algorithms are in the order that I introduced them, so they get more expensive as you go, but not much more expensive. The binomial graph is here, and the binomial tree, or sorry, the repair tree is most expensive in this particular case. So if we have errors, these expected 12-hour errors, so 3 errors, it is basically the same. So that's the major insight. But now I have shown you all these gossip algorithms and the correction, how to correct those algorithms during the runtime. But now let me show you an interesting trick, how you can take a tree and also run a correction protocol. So this is now a different research work. Actually, this was discovered by Martin Küttler in Dresden. If you number the tree right, and you have here the correction ring, and here is the binomial tree for this particular algorithm. So let me just walk you through it. You will immediately understand it with an example. So node 0 starts here. Of course, these nodes are equivalent. Here's these numbered nodes. It sends a message to process 1. And then process 1 fails. So process 1 is not sending the message on. In that whole subtree is now disabled down here. And that's a problem. But we'll see it's not such a bad problem. Then node 0 sends to its next neighbor. So here in the ring, it's here, and in that graph, it's here. Then these 2 nodes that received the message like in the tree shape send it on to the next ones. These 4 nodes that have received the message now send it on. So the 2 nodes are located here. And then the next 4 nodes is this frontier on the right side is located here. And now you see, due to the numbering of the tree, which is quite interesting, quite nice. So we have an exact spacing of 1 here for that subtree. So if we now run the correction protocol, everybody sends to its right neighbor, we will correct that whole tree in a single step. In fact, for any failure in that tree, you will be able to correct it in a single step. In fact, for k failures, you will need k steps. So this is quite amazing. It's an absolutely wonderful algorithm, and it reaches somewhat the lower bound in terms of messages because you only send these 3 messages, and also latency. So this is much better than the gossip algorithm. Here we run it on a real machine. So we benchmark it on a real supercomputer. Again, the latency versus the number of processes. So this, the red line here is somewhat the optimal. So this is the optimized implementation of Cray. So it's a Cray machine that is not fault tolerant. So it will just crash and burn if there's an error. The binomial tree algorithm is here, so it's very close. And then you can see the gossip. It's about a factor of 2, well, slightly less than a factor of 2, worse than the binomial tree that I just showed you. We have not been able to choose. We can actually close this gap here. But Cray is not documenting everything, so they use very low-level interfaces that we don't have access to implement a lot of engineering tricks. But the binomial tree that we have is actually not significantly faster, not significantly slower than this tree, because it's the same tree, it's just differently numbered. So it's an ingenious idea that somewhat closes that area of research, I would say, for broadcasts. But now the question is, what do we do with these 17 other algorithms? So if you're interested in this, I would highly recommend to look at many of these algorithms. How can we make them, how can we make those fault tolerant? And what I find even more intriguing is how can we move this principle of having the correction phase in addition to an optimistic communication phase, either probabilistic or deterministic, but have these two phases. So we run the algorithm. If things fail, okay, we ignore it, and then we correct it later. I think that is a fundamental principle that we could use in many, many, many different contexts, at least in the context of collective operations. In fact, Martin is continuing looking at all reduce and reduce operations and many other collectives, and he's quite successful. So watch out for his publications in the future. But now let me switch gears a little bit and show you a nice picture. Now the question is, what does this picture really mean? So why am I showing you this picture? It's actually, this picture is a data center in beautiful Norway. So let me talk a little bit about the economy of scale in the context of large scale computing. And then we cannot avoid mega data centers. So mega data centers are the future of computing. They're already the present of computing. Like talking to you through Zoom, we are using data centers. Well, if you're watching this video online, you're using you're using a data center that streams it. So this is the beautiful village of Ballangen on the left side. This is north of the polar circle. It has a relatively small population. There used to be a mine there, but unfortunately the mine was closed recently. And this is, on the right side, the Kolos data center. It's actually mostly a mine, so they reused the old mine. It's 0.6 million square meters. This data center is planned to operate at 1 gigawatt of fully renewable energy by 2027. And it has access to fjord water and the cold climate for cooling reasons. So one of the nice observations is that we can put these nice data centers in a nice area. Well, okay. But for data centers, a nice area really means it has to be cold for cooling, energy has to be cheap, and property has to be cheap, and it should be safe of natural disasters. So the perfect location is Norway. And they can actually operate this data center much, much, much cheaper than anybody else could in any other location. And the location of the data center does not matter if the center has a good connectivity to the outside world. Of course, there's a latency factor, but not all applications are latency critical. For example, streaming that video is heavily buffered. You can basically stream it from anywhere on the planet. As long as you have enough bandwidth, you don't worry about latency. Of course, if you want to have a live conversation or play a video game, then this is a different discussion. But many of the workloads we can actually place anywhere on the planet into those mega data centers that this is where this is going to be one of the largest that humanity is planning. And in fact, it's already partially established. So why am I telling you this in the context of an HPC or large-scale computing talk? Is basically because you can observe that the traditional high-performance computers are actually converging with data centers, mostly for cost reasons, cost and efficiency reasons. And so I would say data centers are not supercomputers yet, but eventually they will be. Eventually all of the supercomputers will move into mega data centers just for efficiency reasons. So let me elaborate a little bit on this. So a supercomputer is a machine that has to be fast and cheap. Common misconception is that supercomputers are very expensive. They're not very expensive compared to the performance they get. They're very expensive per unit of size, but that's just because they are 10 times more compressed, so to say, in real space than typical data center computers. But they're relatively cheap for performance. For the data center machines, they have to be cheap, but they don't care too much about performance. It's actually cheap is the major worry of these operators. So here in the supercomputer side, we have performance first, productivity second. On the data center side, we have productivity first, performance second, but still very, very close for large workloads. Both of them are accelerated and specialized. One is accelerated for performance reasons. The other one is accelerated for cost reasons. Both of them are using some form of large-scale distributed memory. So here on the left side, we have traditionally distributed memory, like I mentioned with the MPI programming model, which is not very popular in the data center area. But actually the data center area is a sea of nodes somehow that is growing growing together much stronger. And then the fault tolerance is a big difference. And this is a huge difference because in HPC, we can use checkpoint restart. And in the data center, where we can lose data because we can just recompute it. And in the data center, no data may ever be lost. No credit card transaction should be lost. So now I'm claiming that these data centers will eventually become supercomputers, and supercomputers will become data centers. So the architectures are converging. We will not have two different classes of architectures. We will just run different workloads on the same architecture simply for cost reasons. And my claim is that the network will unify the two. Specifically, a technology called RDMA, Remote Direct Memory Access, is affordable fast networking and offers us distributed memory for free, and also has acceleration properties. So data centers are embracing this technology that is coming mostly out of the HPC field. So Amazon EC2 is doing this, Microsoft's RDMA data center, and Microsoft is employing RDMA. So really, there are new research opportunities that I just want to give you a little bit of an insight in the last couple of minutes of my talk. This is again going to be a whirlwind tour across many papers. You will find the references at the bottom of the slide if you care to dive deeper into any of those topics. So this is one big research opportunity. In fact, post-RDMA networking and smart NICs, which is the next step after this, is most likely going to win the data center as well as the supercomputer. But that's a different talk, a different keynote I gave last week. So that doesn't fit here very well. But if you're interested, you could look at that as well. It's on YouTube. So what is RDMA now? So RDMA is really an architectural extension that my CPU, which has load store access to my memory, so it can read values from memory, from its own memory, like I explained in the MPI case, but it can now actually, through the PCIe root complex, use the NIC to read values from remote memory. And that is quite interesting. So I can now read a memory location at an arbitrary location in the data center, right? So I can go to another node and read its memory. So in this sense, a data center now has, a computer in a data center has not only 64 gigabytes of memory, but it has actually 64 terabytes or 600 terabytes, depending on how many machines I have in the data center. So I have a wonderful scalable applications. One of the problems here is that the memory model that this NIC offers, because it runs asynchronously to the CPU, is a little bit unintuitive. So if you look at this execution here, where if I x equals 0 and y equals 1, I have two processes. Get is basically read. So I'm reading from y at process 2 into x, and then I'm assigning x equals a. Here I'm reading x on the other side. So I'm technically reading a 0 here. I'm reading a 1 here. Then I assign this to b. But now you observe that a equals 0 and b equals 1. And then you're like, what? That is not because I'm reading from over here and I'm reading from over here. That should not be the case. It should be a equals 1 and b equals 0 if it was sequentially consistent. Unfortunately, this networking interface, this RDMA interface, is not sequentially consistent. So here's an explanation with relations where we could now prove this, that this can actually happen. I don't have enough time, but it's quite obvious because this read of x happens up here. So it's actually reading from this value. This read of y may be reading from this value, and this get may execute later, right, as you can see in this diagram here. So actually we have full axiomatic semantics published at UPSLA 16 for various interfaces that are successful in the area, so including MPI3 RMA, but many others as well. And then if you want to go more into details, you could read that paper. But I just want to tell you it's not as simple. But now we can take these semantics and build new algorithms, new distributed algorithms, where we are somewhat assuming this distributed memory style programming model without passing messages, but reading direct memory on the other side. So here we implemented a direct access replication protocol, which is really a consensus protocol over RDMA, where we have a state machine running over an RDMA implementation, where we directly access the log in the memory of the other machines. We directly access heartbeat data. We directly access configuration protocol. So it's actually taking the Raft algorithm and moving it to an RDMA system, which gets us a huge speed up. So here, compared to Zookeeper, we're either 22 or 35 times lower latency. So these RDMA technologies are blazingly fast. I can go through the data center in 1 or 2 microseconds, and this will just be faster. Messages take me at least 10 or 15, maybe 30 microseconds. So this is a huge potential performance gain for this replicated state machine implementation. Then you can, of course, do the same, apply the same principles to other things. For example, distributed databases become hot again because now we have the networking to actually support the distribution. So we have run some experiments with join, of course, different types of join. So direct radix join as well as sort merge join. They and implemented them over RDMA on the large scale cluster system. And what we see is that actually we can scale the join to thousands of cores with billions of tuples per second throughput. In fact, that is a record that nobody has beaten yet. So in our system, we could just run it on a larger cluster to get even a higher throughput for these operations. For these different join operations, so radix join and sort merge join. And here's a breakdown of where the time is. In fact, the time is really in the network partitioning phase as it goes up with more cores. So really the network is somewhat still the bottleneck, but it's a much lower bottleneck than it used to be. So now, if we know that we can do that we can have a very low latency interconnect, we could actually do concurrency control across the whole data center. Imagine having 10,000 or 100,000 machines working with a single lock. Of course, now you immediately say, well, that's extremely non-scalable because a single lock is granting access to a single object. But now if you use reader-writer locking and if you have a very low write frequency, then this could actually work. And what we developed is a protocol for locking full data centers here. Again, the reference is at the bottom. So we have a distributed servers, then these are packed into racks, and these are packed at the full data center protecting a single lock. So the lock is a modular lock. It's based on the MCS lock, so where we have multiple writers and multiple readers, but it's an extension of the MCS lock. So the writer lock is an MCS lock, to be precise. So all these writers, they have lists. These lists are carried to the next hierarchy level. So it's really the same as the standard MCS lock, and they're carried to the top level. And then at each level, one is winning and moves up. So these MCS queues or lists, they form really a distributed tree that is distributed across the whole data center. So now this is, imagine this is 0.6 million square meters where your lock is covering. And then we of course have reader locks as well. And these readers and writer locks, they synchronize with a distributed counter. So we do have a counter at each node, which counts whether there is a writer, or it counts the number of readers that arrived at the critical section. And then it also counts the number of readers that have left the critical section for fairness reasons, because at some point you want the writer to get access to the critical section. So here, there are some parameters that I don't want to go into detail, but basically we can share this counter across multiple nodes to make it more scalable. So it's a shared counter now across these two nodes. We could also have individual counters like I mentioned before, but then we need to check more counters in the tree protocol. So in fact, this lock opens a design space that is non-trivial, where we can trade off the maximum number of consecutive lock passings between reader. We can trade off the throughput of writers versus readers. We can trade off the latency of writers versus readers, and we can trade off the fairness of writers to be either locally past the lock or past the lock to the next hierarchy level. So all of these now enable different lock designs, and it's actually quite powerful. So we use that idea, this lock idea, to implement two-phase locking on a database, this distributed database system again. And we discovered that actually all of this loose consistency database business that Google namely started a while ago, saying, oh, we cannot afford consistency on a large-scale data center, is basically invalidated by the developments in networking. So we implemented a fully consistent database with two-phase locking, like basically in a textbook, applying some of the principles I mentioned before, like you would find in a textbook. And then we can run 38 million transactions per second on 2,000 cores. So this is way beyond what you actually need. In fact, we also show that if you scale the latency, here we scale the latency versus the throughput. If you use InfiniBand, which is a 1 microsecond latency, and AWS's current network has a 16 microsecond latency, you gain about 40% throughput. So the network latency is incredibly important, but we have these systems today that are actually working pretty well for this. So now let's step a bit back. So now we have the data center, we have large scale locking, we have replicated state machines, we have large scale joins. So we have all of the bits and pieces we can put together in the data center to apply HPC principles to that. But now back to the CDACs. Isn't it still all a communicating number of these nodes? And yes, it is. And this is really the last piece I want to present. This is basically the work that is going on right now. We want to understand how to program the large data center directly. So we want to cut MPI out of the game. We want to see the computation as these nodes, in fact, as the generators of these nodes. So here we start from a domain-specific language. It may be a database language, but in this case, it's a Poisson equation that a computational scientist is using, writing code in Python. We compile this to a graphical representation of the generating graph. So not the full CDAC, not all of these nodes we are seeing, but the graph that generates these CDACs. And then we can execute this graph, and then of course we get to the full computational DAC, which now may have trillions of vertices. This is an O of 1 representation because it's still the same size as these as the input program itself. And now we can optimize this graph to different target devices, multi-core CPUs, GPUs, and FPGAs, or even direct hardware design. So I don't have enough time to cover this, but imagine the possibilities that we have with manipulating these graphs now. Now we represent the structure of a program as a parametric computational graph. Now we can define cuts of this graph. Now we can define transformations of this graph to map it to RDMA, to map it to the topology. All of these things that I told you before, you can now apply to these parametric graphs. And this is our current research. This is the DACE program together with the DAP implementation. The DAP program together with the DACE implementation. And I'm happy to answer more questions on this in the question session. But I also want to mention that we are hiring. So if you're interested in programming and large-scale systems or anything that I mentioned, please let us know. And with that, I would like to conclude my talk, and I'm open for questions. Thank you.